In this video, we are going to solve the study problems from the first chapter of Introduction to Polymer Science by Leslie Sperling. Polymers are obviously different from small molecules. How does polyethylene differ from oil, grease, and wax, all of these materials being essentially CH2? So, oil, grease, and wax vary in the number of carbons in the chain. Oil and grease have about 16 to 25 carbons in the chain and they are high viscosity liquids. Wax has about 25 to 50 carbons in the chain and it is a crystalline solid. Okay, the second problem, write chemical structures for polyethylene, polypropylene, polyvinyl chloride, polystyrene and polyamide 6,6. Polyethylene has two CH2 groups in a mer. So you can write it like this, or you could also write it with just one methylene group. Polyvinyl chloride is the same as polyethylene, but it has a chlorine substituent. Polypropylene has three carbons. One of the carbon is a methyl substituent. Polyamide 6,6 has an amide group formed by an amine and a carboxylic acid, each of them having 6 carbons, which is why it is called 6,6. So the amino group is a hexamethylene amine and the carboxylic group is a adipic acid with 4 methylene groups and 2 carbons coming from the carboxyl group. Polystyrene again an ethylene group with a phenyl substituent. Name the following polymers. The first one would be poly followed by 1-methoxycarbonyl ethylene. There are two carbons in the chain, so it's ethylene, and this group is methoxycarbonyl. So poly 1-methoxycarbonyl ethylene. Also called as poly methyl acrylate. The second one, poly There's a methyl group and a ethoxycarbonyl group. So ethoxycarbonyl group goes first. 1 ethoxycarbonyl, 1 methyl ethylene, or polyethyl methacrylate. Methacrylate because there is a methyl group. Poly 1-acetoxy CH3COO group is 1-acetoxyethylene, or polyvinyl acetate. The last one, poly 1,1-difluoroethylene. There should be a parenthesis here. What molecular characteristics are required for good mechanical properties? Distinguish between amorphous and crystalline polymers. A plot of the tensile strength of polymers to molecular weight is like this. At very low molecular weights, the tensile stress to break is almost zero. As the molecular weight increases, the tensile strength increases. And since the major point of weakness at the molecular level is in the chain ends, because they don't transmit the covalent bond strength, the tensile strength reaches an asymptotic nature at infinite molecular weight. So we can say that as molecular weight increases, tensile strength increases. Also, a narrower molecular distribution yields better properties because the low end of the distribution may act as a plasticizer or for softening the material. So, narrow molecular weight distribution also gives good properties because the low end acts as a plasticizer, softening the material. If we consider paraffin wax, which has about 25 to 50 carbon atoms, the structure is like this. It's crystalline and it's held together by only by van der Waals forces. If you consider a longer carbon chain, about 100 carbons, it's still held like this. It is again held by van der Waals forces. However, if you consider polyethylene, which has a very high molecular weight, it has a structure of a lamellar structure which has crystalline portions in which with chain folds, and then there are some amorphous regions followed by again some crystalline portions. These are the chain entanglements, and so these are the amorphous portions. Crystalline polymers have crystalline structure with amorphous regions as well. Show the synthesis of polyamide 610 from the monomers. So polyamide 610 can be synthesized using a diamine that has 6 carbons and a diacid that has 10 carbons. So the first number denotes the number of carbons in the amine, and the second number 10 denotes the number of carbon atoms in the acid. So this is sebacic acid, and this is hexamethylene diamine, and that will condense, eliminating molecule of water. So two molecules of water are eliminated from either side, and this is nylon 610. Instead of the acid, one could also use the acid chloride. So this is sebasoil chloride, and this condenses to give you nylon 610. This time with an elimination of two molecules of HCl between them. Name some commercial polymer materials by chemical name that are A. Amorphous, cross-linked and above Tg. B. Crystalline at ambient temperatures. Amorphous, cross-linked and above Tg would be rubber band, which is known by the commercial name cross poly butadiene styrene. It's a copolymer of butadiene and styrene, a statistical copolymer. So that is amorphous and cross-linked above its glass transition temperature. For crystalline at ambient temperatures, we could have cellulose, which is also called by the commercial name rayon or cellophane, and that is crystalline at ambient temperatures. Draw a log modulus temperature plot for an amorphous polymer. What are the 5 regions of viscoelasticity and where do they fit? To which regions do the following belong at room temperature? Chewing gum, rubber bands, plexiglass. On the y-axis we have log of Young's modulus, and the x-axis we have temperature. and the graph is something like this. This is the glassy state. This is the glass transition state. Here is the rubbery plateau. Here is a rubbery flow. And this is the viscous flow. Chewing gum belongs to the rubbery flow area at room temperature. Rubber bands belong to rubbery plateau. Plexiglass is polymethyl methacrylate, PMMA, and that belongs to it's below the glass transition temperature at room temperature, so it belongs to the glassy state. Define the term Young's modulus, tensile strength, and chain entanglements and glass rubber transition. Young's modulus is the ratio of stress to strain. A high Young's modulus means the material is stiff. Tensile strength is the maximum load a material can bear before its breaking point. Chain entanglements. When the polymer chains are short, there are no entanglements among them. For large polymer chains, these chains can entangle with one another, and that's called chain entanglements. The transition between short polymer chains and chains at which entanglements begin is often at about 600 atoms in the backbone of the polymer chain. Glass rubber transition. In the glassy state, the polymer is stiff and brittle. As the temperature increases and the glass transition temperature happens, the polymer softens. The Young's modulus falls about 3 orders of magnitude and it becomes rubbery. This is a glass rubber transition. A cube 1 centimeter on a side is made up of one giant polyethylene molecule having a density of 1.0 gram per centimeter cube. What is the molecular weight of this molecule? Assuming an all-trans conformation, what is the contour length of the chain? Length of the chain stretched out. Mer length is 0.254 nanometers. Volume is 1 centimeter cube and density is 1.0 grams per centimeter cube, which means the mass is density times volume, which is 1 gram. So since this is the mass of one molecule, this is the molecular weight. So this answers the first part. Assuming an all-trans conformation, what is the contour length of the chain? So for polyethylene, the all-trans conformation can be written like this. The wedge shows that the hydrogen is coming out of the plane. and so on. To find the contour length, let's see how many mers are there in this polymer chain. So each mer is CH2. It's getting repeated n times. (14 grams per mole) because carbon is 12 and 2 hydrogens is 2. So 14 grams has 6.023 times 10 to the 23 mers because it's 14 grams per mole. So 1 gram will have 6.023 times 10 to the 23 over 14, which is 4.30 times 10 to the 22 mers per gram, and in this case 1 gram is the molecular weight. So contour length is the product of the number of segments of the polymer molecule and its length. So we have 4.30 times 10 to the 22 mers. So we have 4.30 times 10 to the 22 minus 1 segments because each of this is one segment. So between 3 carbons we have 2 segments. So between 4 carbons we have 3 segments, and so on. Contour length is going to be 4.30 times 10 to the 22 mers times 0.254 nanometer, which is given as the length of 1 mer. So that will be, if you multiply, we get 1.09 times 10 to the 13 meters. So that is the contour length of this giant polyethylene molecule.